Hi, my name is Dorde Zivanovic. I'm a PhD student at the University of Oxford. I will present the paper Given QR decomposition over relational databases. This paper is an equal joint work with my PhD advisor Dan Olteanu and Nils Vortmeier, both from the University of Zurich. Relational data is highly relevant in data science. According to Kaggle surveys, most data scientists use relational data at work, particularly in retail, marketing, insurance, and finance. It is therefore important to enable data science over relational data. At the heart of data science is linear algebra. In this work, we consider a fundamental linear algebra problem that spans through data science and in particular machine learning techniques, the QR decomposition of a matrix. Our goal is to enable the efficient computation of a QR decomposition for relational data. A standard approach to machine learning over relational data would be to use a relational database system to keep the data. When data is required, it is exported from the database system in the form of a data matrix. This typically involves joining the relations of the database. Then the data matrix is imported into an external tool. However, this has significant flaws. First, the data matrix might be much larger than the original relations. Besides creating and storing this matrix, also moving it from one system to another can be very expensive. Moving the computation closer to the data is far preferable. This is what we are interested in. This work we show how to combine the computation of a QR decomposition, a linear algebra task, with that of joins, a relational algebra task. Our approach pushes the QR decomposition computations past joins, so that it only takes time proportional to the size of the input database, rather than the size of the potentially much larger join output. As for simple aggregates, like count and sum, you can achieve a linear runtime in the size of the input relations, in case the join is acyclic, so admits a join tree. Let me introduce the QR decomposition. The QR decomposition of matrix A is the product of two matrices, an orthogonal matrix Q and an upper triangular matrix R, such that Q times R is A. For the orthogonal matrix Q, holds that Q multiplied with its transpose is the identity matrix. In the upper triangular matrix R, all entries below the main diagonal are zero. QR decomposition can be used, for example, for computing the least squares solution in the system of linear equations Ax equals b, obtaining the Cholesky decomposition of the matrix A transpose A, and computing the singular value decomposition of the matrix A. For many applications, only the matrix R is necessary, and we are mostly interested in computing this matrix. Also, usually, it is not necessary to compute the full QR decomposition, but the thin decomposition is sufficient, where the all zero rows of R are discarded, together with the columns of Q that are only multiplied with these zeros. So from now on, in the QR decomposition, for us, the matrix R is a square matrix. The number of columns in the matrix Q is the same as for A and R. Standard approaches for computing R work on the materialized join. We propose an alternative, an algorithm we call Figaro, which computes the QR decomposition based on given rotations and operates directly on input relations. So it pushes the computation of R past the joins to the input database. It takes linear runtime the number of tuples in the input database, instead of having a runtime that depends on the size of the materialized join. It is equivalent to the application of given rotations to the materialized join. If necessary, Q can be obtained efficiently from R and the input database. QR decomposition can be computed using so-called Givens rotation as follows. One Givens rotation is used for each entry below the main diagonal to set this entry to 0. Consider we would like to zero out the value 4 in the fourth row in this matrix. For this, we pick another value in the same column, say 3. Together, they form the vector 3, 4, which we depict here in the coordinate system. Now there is a rotation by some angle theta that rotates this vector such that it lies on the x-axis, so setting the second component to 0. This example, the resulting vector is 5, 0. Given rotation applies the rotation by some angle theta to two rows of our input matrix, here to the third row and the fourth row. This rotation is encoded by multiplying our rotation matrix from the left to the input matrix. In the resulting matrix, the vector 3, 4 is replaced by vector 5, 0, producing a new 0 in the matrix. Also, the remaining values in the two rows are changed. Repeating this for all values below the main diagonal results in the matrix R. The multiplication of all rotation matrices gives us the matrix Q. To obtain the upper triangular matrix R, the classical Givens rotation algorithm applies rotations for each value below the diagonal. In our case, this takes time linear in the number of rows and quadratic in the number of columns of the material echelon. Here, the square is because each rotation takes time linear in the number of columns, since all values in the two rows must be changed. Figaro, on the other hand, applies blocks of transformations directly to the input relations, which are equivalent to long sequences of Givens rotation. When performing QR decomposition over a cyclic joint, Figaro only takes time linear in the number of tuples in the database, which may be much smaller than the number of rows in the material echelon. As a result, Figaro can be much faster than the standard Givens rotations algorithm, as well as any QR decomposition approach that needs the join of the input relations to be materialized. Figaro also has far fewer rounding errors than standard algorithms because it performs far fewer operations. In our experiments, Figaro is up to 3 orders of magnitude faster and 3 orders of magnitude more accurate than the leading competitors Intel MKL and Open Plus. Let us see a simple example of how Figaro works, using a Cartesian product of two relations. Its size is quadratic, yet Figaro can compute the upper triangular matrix R time linear in the number of tuples in the two input relations. We color code the tuples in the two relations to better trace how they are changed. We will represent the value 0 by white boxes. This is now a Cartesian product of the two relations. As we can see, the first tuple of the first relation is paired with each tuple in the second relation. Same for the other tuples in the first relation. Let us focus on the first block of tuples in the Cartesian product, formed by the pink tuple from the first relation and all tuples from the second relation. Our first goal is to zero out all but the first occurrence of the pink tuple. The first key observation is that the Givens rotations that achieve this do not depend on the actual value of this tuple, but only on the fact that all occurrences of the pink block stand for the same value. For example, consider the first rotation. The angle of this rotation is defined using a vector that has the same value as its first and as its second component. All vectors of this orb have the same angle with the x-axis, so the angle of this rotation is some constant. It follows that the new value for the first occurrence of the pink tuple that we get after zeroing out the other occurrences only depends on the value of the pink tuple before and on the number of occurrences, and we can compute it easily. Tuples from the second relation are also changed by these rotations, but the new values only depend on the old values and not at all on the first relation. We can also compute them easily from the second relation. The second key observation follows. When we apply the same sequence of rotations to each of the remaining blocks of tuples in the Cartesian product, the effect is that again, all but the first occurrence of each tuple from the first relation are zeroed out, and equally important, the same changes to the tuples from the second relation are produced. When we look at the right column of the resulting table, we observe a similar pattern as we had before in the left column. We have 4 values that each are repeated 4 times. We can similarly as before apply the rotations to these repetitions and zero out all but the first one. As in the step before, the values that occur can easily obtained from the values that occurred after the first step. In summary, we observe that the non-zero rows we get after repeatedly applying rotations can be obtained directly from the input relations without the need to first materialize the product. As we want to compute the upper triangular matrix R, we are not done at this point. The non-zero rows in the obtained matrix do not yet form an upper triangular matrix, but the number of these non-zero rows is only linear in the size of the input relations. This means we can continue with the standard algorithm to further zero out linearly many entries to obtain the desired upper triangular matrix. We now present some of our experiments. Further details are in the paper. We consider both runtime performance and accuracy experiments. One experiment follows the simple example we just discussed, the case of a Cartesian product of two relations S and T. Here, we vary the number of rows and of columns of each of the two relations. We depict the speedup of each figure over the competitor Intel MKL in a heat map. White regions mean that MKL did not finish for this configuration. We see that as the number of rows of the two relations increases, so does the performance gap between Figaro and MKL. This gap increase is up to 3 orders of magnitude, which corresponds to the increase in the gap between the size of the Cartesian product versus the size of the two input relations. We also investigate the accuracy of the algorithms for the same Cartesian product. In the literature, accuracy is typically measured by checking how far the computed matrix Q is from an orthogonal matrix. We propose an additional accuracy measure based solely on the upper triangular matrix R. For this, we choose an upper triangular matrix R fixed with values that can be represented exactly on the machine. We do reverse engineering and construct input relations S and T such that QR decomposition of their Cartesian product yields an upper triangular matrix R that contains R fixed. We can then check how far the computed R fixed is from the chosen R fixed. Using a heat map again, we show the accuracy gap between Figaro and Intel MKL. And again, as we increase the number of rows in the input relations, Figaro becomes up to 3 orders of magnitude more accurate than MKL. The main reason is that the number of rounding errors of both algorithms is proportional to their runtime, and as we have seen before, there is a corresponding gap between the runtimes of the two algorithms. However, as we increase the number of columns, the magnitude of rounding errors gets closer for the two algorithms, shown in the right of the heat map. The next 3 slides depict the runtime performance of Figaro versus MKL for 3 real-world datasets. The following plots show the runtime as a function of the fraction of the materialized join that we consider, from 10 to 100% in steps of 10%. The first dataset is retailer. It has 6 relations, one large relation of about 84 million tuples. All joins are key-for-in-key joins and form a snowflake schema. The size of the materialized join is about 10 times larger than the input database. This size gap translates into a 3 times runtime performance gap between Figaro and MKL. The second dataset is Favorita. Here, the size gap between the join and the input is about 6 times, yet Figaro remains at least 10 times faster than MKL. The third dataset is Yelp. Here, the size gap is very large, over 300 times. This as well translates into a large runtime gap. Let us conclude. In this work, we introduce Figaro, an algorithm for a QR decomposition over joins of relational database. Figaro exploits the structure of the join to push down the computation of the upper triangular matrix past the joins, so that for a cyclic joins, its runtime is linear in the size of the input database. This performance benefit also translates into an accuracy benefit, as Figaro does fewer rounding errors than an algorithm that relies on the join materialization. Key ideas behind Figaro are also applicable to further matrix decompositions defined by relational queries. We are currently doing this for ALU decomposition. Decompositions such as Cholesky and SVD can be readily recovered from the QR. Thank you for listening.